So our goal is here, we have many records with wine data, and we want to identify, to predict if it's a white wine or it's a red wine. So our outcome variable is a categorial variable. And that makes it a little bit more different. And we want to use for this logistic regression. I will start with linear regression just to explain the principle a little bit easier. But keep in mind, linear regression is not a good tool to evaluate categorial variables. So we did that last time. So I load my packages here, the tidyverse, models. This one determines that the one class, the one that I code with the one, is my positive class. I will comment on that a little later, but I execute it here. I need these packages here, glmnet for logistic regression later on, read R to read my data, Jitter to make the variables a little bit nicer, and the tidyverse. And I load my data here. I make sure I reset my random number generator, and we can look at the data here. And these are more than 3,000 wines. They're either red or white. And I have a lot of chemical properties here. And I have to say, I'm not a wine expert. I would not be able to look at these properties and determine if it's a white wine or if it's a red wine. And I assume most of you wouldn't be able to do that either. But the machine learning procedure will be able to do that pretty well. Well, machine learning procedures cannot deal very well with characters. So we have to make this one here either a dummy variable or a factor variable. And I will tell you later on what a factor variable is. For now, stick with the dummy variable. And for the regression, we want actually a dummy variable. So I split my data set into training and test data. I want 85% to be the training data. This here. And I use the recipe. And I'm starting with using sulfur dioxide to predict if it's a red wine or if it's a white wine. And I want to keep my data set simple. So I want only the wine color in my data set and the total sulfur dioxide, these two columns. And I use the split, use the training data, and I use the split here. So build the recipe based on the training data, what we again almost always do. And the dummy variable, I have only one categorial variable, and that should become a dummy variable. Do it here. And that will generate a variable that is called wine color underline white. That means if it's a 1, it means it's a white wine. I don't like the spelling here so much, so I rename it in wine color white. That's a matter of taste. It's not needed to do. And then I prepare my data. This one here is optional. And I execute my recipe.
Professor?
Yes.
Somebody in the comments mentioned, why did you use Strata for
I use Strata.
Wine color? Sorry.
Yes, I use Strata. Thank you. Why did I use Strata here? I don't have to use it. It works just fine if I use it without it to state. So this one just works fine. I decided to use it because it makes sure that in my training data set and in my test data set, that I have as many red wines in my test data proportionally, percentage-wise, as many red wines in my training data set as I have white wines. If I don't use it, and I'm unlucky enough, it could happen that I have a high percentage of red wines in my training data, but a low percentage of red wine in my testing data. And that would cause complications. So I run my recipe here. Let's go back. I run my recipe. And now I assign the data based on the recipe to my training data and to my test data. And I will only use the training data to optimize the model. I can use a juice command because the training data are already hidden in my recipe. And I use the bake command to apply the recipe to new data, in that case, to my testing data. As a consequence, I have training data and test data. You can see it here. 478 test data that I will use to evaluate the quality of my model, 2,700 about training data that I will use to optimize it. And again, I use linear regression first, which is not the best choice. We will use logistic regression later on, which is a far better choice. So I want to use a linear regression model. I always have to determine the mode, and that's a regression here. It's not a classification because regression models can't do classifications, at least not in these settings here. I use the LM, and here's a fit. Wine color is my output variable. Total sulfur dioxide is my predictor variable, and I use the training data set, of course, to optimize the model to find my B0 and B1 that minimize the error. Execute it, and done. I generate plot data that I want to later plot. How do I do that? I use the model here, pipe it into the predict command, so it would go where the cursor is. And then I say, use this model on the training data set to predict the outcome variable. Then I connect the predictions together with my training data and put that all in the data set plot data OS. What is more important is that you understand what is in there. I'll show it to you. These are our training data. And you can see, if you look at the first record, the wine has a sulfur dioxide level of 37 units and it's 0. That means it's actually a red wine. Remember, our positive class, the one that we predict and code as 1, is a white wine. This wine has a 14% chance of being a white wine. That is less than 0.5. So we consider this prediction as being 0, as being a red wine. And you can see this is correct. It's problematic to interpret these numbers as probabilities, but we will still do it, and you will see the problems in a little bit of a time. Let's look at number 3, record number 3, that has 139 units of sulfur dioxide. It is actually a white wine, and the predicted probability for being a white wine is 80%. So if we consider that as white wine prediction, rounding it up to 1, then we can say this actually is a white wine. When we look at record number 2, we can actually see the problem of using the predictions as probabilities. We have a predicted probability for being a white wine here of 127%. That's ridiculous. Everybody knows probabilities go from 0 to 1. Well, if we're generous and round this down to 1, we can say this wine has a very, very high likelihood of being a white wine. 127%, or we round it down to 1. I can also end up with predictions that are negative. Let me see if I see some here. Here. This wine has a very low sulfur dioxide content, and it is predicted with negative 5%. Probabilities are not negative. So I treat this here pragmatically as a low number, and a low number, low probability of almost 0, is considered not to be a white wine, and therefore it's a red wine. Prediction is actually correct, but this is kind of weird because probabilities are between 0 and 1. But we live with it for now. Let me plot the data. We did that before. And I don't want to comment on the ggplot commands. They're super powerful. I strongly recommend to take a tutorial. These are our data. These are our 3,000 wines. And very difficult to read diagram. Why is that? Because here are all our white wines, and they kind of lay on each other. You can see it here. These are clearly not 3,000 points that you can see. That is because so many lay on top of each other. There's a trick to deal with it. And this is to create a jitter plot. You just have to be careful when you interpret it. You can see that as if you would shake the diagram vertically. And then what happens is the points kind of leave their real position. Here is the 1. All these points are white wines. They are all on the 1 line. But by shaking them, they got a little bit higher and a little bit lower. What is important to note that although not all the points are on the 1 line, their value is actually 1. This has a value of 1 and not of 0.75. This one has a value of 1 and not a value of 1.25. It's just located there so we can see the dots a little bit better. Same here. All these have a value of 0, but the points are located a little bit away from the 0 so we can see them a little bit easier. That means, because all these variables have a value of 0, these are the red wines. And all these ones have a very valuable value of 1. So these are the white wines. And now you can get the idea, why not putting a straight line through it to estimate if it's a red wine or white line? And I do this here. I run a regression, or I use the results from the regression that I did already run. And here we are. Here is actually our regression line. Goes through there. So now we can use the regression line to predict. So let's say we have a wine that has a sulfur dioxide level of 100 units. Then I go up to the regression line, go to the left, and I get a value bigger than 0.5. And I predict this wine to be a white wine because the probability is higher than 0.5. White wine is our positive class. That's the one we predict for. So I would say it's a white wine. And here I color coded the whole thing a little bit. And you can see it easier. Let's first look at the regression line. The regression line starts here and goes up like before. What you can see, it has 2 colors. And what I did is, whenever the regression line leads to a value that is lower than 0.5, the regression line is painted in red because it would predict not a white wine, and consequently it would predict a red wine. Whenever the value is bigger than 0.5, the probability for a white wine is bigger than 0.5. We say, yeah, we predict a white wine. Then it's here in a bluish color for the white wines. And you can see which wines are predicted white. These are these wines here. And these wines down here. Well, there's a difference between these 2 blue clouds. These wines here actually have a value of 1. They are actually white, while these ones have a value of 0. They are red. They are wrongly predicted. I can see here also all these wines here are predicted as being red because they are in the area where the regression line produces a value smaller than 0.5. So all these here are predicted as being red wines. But these wines here, they are not red. They have a value of 1. That means they are white wine. So these ones are predicted wrong, while these ones are predicted right. You can see already that most of the wines are predicted correctly. So we did a pretty good job. I saved the coefficients of the regression. And it's just like any other regression, see? This one here would be the B0. This one would be the B1. And I can generate a confusion matrix. And the best way is we look at the confusion matrix. And I do that for the test data. And we don't have to go into the code in detail. I print the confusion matrix. And here's a reminder. Our positive class is number 1. And we can see already the truth is in the column. That means everything that is in this column is a red wine with a 0. Everything that is in this column is a white wine. These are just the facts. The columns represent the facts. The rows represent the predictions. So let's look at the first column. In the first column, 1,218 wines were actually red, and they were predicted as red. So correct. 142 wines here were red, but they were predicted as white. False. Here in the second column, we have the white wines. Remember, positive class, they are coded with a 1. Well, 180 wines here were white, but they were predicted as being red. That is wrong. 1,180 wines are white, and they were predicted as white. That is correct. So let's look. Correct. Correct. So on the diagonal, on this diagonal, you find the correct results. Why on the secondary diagonal, on this one here that goes the other direction, you find the wrong prediction. And you can see we did a pretty good job. I can do the same thing based on the test data because that is actually the relevant thing. I run my confusion matrix on the test data, and these are the data I have never used to optimize the model. So this is a true test if the model is really right. I print it here, and you can see these ones were right, and these ones were right. You can see even more. We can calculate a few fractions that are very informative, and I will not go into all of them, just into a few of them. So here we are. Change this a little bit. Let's talk about this. And we did that last time, so it should be a review for everybody. Okay, first we could calculate the accuracy. The accuracy is calculated by taking the correct ones, which is 219, plus 211, and divided by the total number of records here. And we have in the test data set 478 records. You can see this here. And the result is we are correct in 90% of the cases. Pretty good. There was a question? Okay. Let's clean it up. I could also focus only on the positive class. So I want to know how many of my white wines are predicted correctly. This is my positive class. How do I do that? Well, I know 211 are predicted correctly. And I had a total of 211 plus 28, so a total of 239. And this fraction, this ratio here has a name. It's called the sensitivity. When I calculate how correct I was percentage-wise based on the positive class, then that is called the sensitivity, and the sensitivity is reported here. So this should be calculated to 88.3%. What I also can do is I can do the whole thing on the negative class. That would be the red wines. 219 red wines were predicted correctly. And I had a total of red wines of 219 plus the 20 that were not predicted correctly. So a total of 239 here. This is a balanced data set. That is a consequence of my strata. So 219 divided by 239 gives me how correct was I percentage-wise on the negative class, and that is called specificity. So I can see I did a little bit better on predicting red wines than I did on predicting white wines. This is why I use these different things. Okay, so much for the linear approach. We come back and look at a better approach, which will be the logistic regression. So we talked about linear regression is not that great for categorial variables. And one thing is it generates, because this line here is not limited, the regression line, it can generate probabilities that are greater than 1. That's weird. We know that they don't exist. And it can generate negative probabilities. That's not a good thing either. So that's bad enough. But what is even worse is shown in this graph here. Let's start with where it works fine. The blue one is our regression line. So here's 0.5. So everything left of this line has a value of smaller than 0.5 and would be predicted as 0. Our positive class is here that the tumor is malignant and the 0 means it's a benign tumor. So all these ones here are considered as benign, while all these ones here are considered as malignant. That's okay. We can live with that. And we saw in our example, we got actually pretty good results. But what if we have an example like on the left side? Our line is here. Our blue line is here. And you would say, well, so what? It's a little bit higher. Where's the difference? Well, everything that is above the 0.5 line will be considered as malignant. And everything that is below will be considered as benign. Well, let's look at our regression line. Our regression line always produces values greater than 0.5. So the whole area, all of these are considered as malignant. And this just doesn't make any sense. So that's another problem we have here with linear regression. So we don't want to use linear regression. Well, it would be nice if we had a line like a linear regression line, but that would be limited to an area between 0 and 1. And this line exists. Let's look at it. Don't even look at the formula. That's a logistic formula here, function. And look how nice it is. It produces like a regression line in this area. It's like a regression line. It produces values between 0 and 1. But when I get very big x values, it becomes horizontal here. And that means it produces 1s, but never anything higher than 1. When the values become very small, the line gets flat and it produces 0s. So this function here, the logistic function, is actually what we would like to have. Take it as a wish. So what is the underlying function for this red line? The underlying function is a little complicated, but we don't have to bother with it. It's E. E is a constant. It's 2.7 something. So it's basically 2.7 to the power of x here, divided by 1 plus E to the power of x. A little nasty. You can probably expect already that our parameters are not that easy to estimate. And it gets a little bit more nasty when we go to the next slide. And that's it with nastiness. So instead of plugging in the x here, this is my regression line here. This is my x. I multiply each x with my b1 and add b0, like I did before. And whatever I get as a value, I use it as an exponent for the e here. Then I divide by 1 plus, same thing again, e to the power of what was before my linear regression line. The only thing what you have to understand at this point is, well, two things. First thing is, this kind of nasty formula produces a function that is limited to 1 and 0. And in between, it's almost linear, like our linear regression line. So that's what we want. Goal reached. And you can see it here. I plugged for this function here. I used a b1 of 0.5 and a b1 of b0 of 3. Well, you can probably imagine that calculating the b0 and b1 that minimizes the prediction error is not possible. We don't care. We have our optimizer. The optimizer with a systematic trial and error process, steepest descent in many cases, finds the best values for b1 and b0. And that's what our logistic regression does. Let's look how it works. We go back to R. And one technicality, you don't even have to understand it, but at least I want to mention it. R can store dummy variables in two different ways. Just as a dummy variable, it's just a number. We did that before. Our dummy variable was just a number as every other number, except that it had only values of 0 plus 1. Or it can store it as what is called a factor. So treat a factor variable like a dummy variable, where the dummy variable is often saved internally. And the point why I'm explaining is that our logistic regression in tidymodels cannot have a dummy variable as a numeric value. It needs the dummy variable as a factor. So these are where these two lines for. It transforms the dummy variable here into a factor. Treat it as a technicality. There is not much to understand behind it. So I adjusted my data set, and if you look at the data set, if you look at the training data, you don't even see a difference. See, it's zero, still 0 and 1s. It's just internally saved in a different way. Now I run my logistic regression here. Let's get rid of this. How do I do that? Well, like before, logistic regression is the name of the model that I want to run. I have to determine the mode. The mode is now classification because it's a factor variable. I set the engine to GLM. That means this is a package where the logistic regressions can be found. And like before, I have to say which one is my dependent variable, my outcome variable, that's a white wine, and which one is the predictor variable, the one that I want to predict. And of course, I optimize my B1 and B0 in these complicated logistic function based on the training data set. And good for you, you don't have to care about the optimization process. That is all done in the background, literally on the push of a button, what I do now. I generate my plot data similar than before, and I can look at them. They look a little bit different than the other ones. The procedure gives me predictions for both, predictions for 0 and 1. These are the predictions I'm interested in. These are the predictions for the positive class. So let's see. The first wine here has a probability, and now I can interpret them as probability, of 5% to be white. That means it's a red wine, because the probability of being white is lower than 0.5. And indeed, it was a red wine. This is what we use here. This is kind of redundant information, because if the chance of being a white wine is 5%, then the chance of being 0 being a red wine is obviously 95%. So looks like in the first ones we do very well, but of course we have to investigate that a little bit more. Before I do that, I go to the ggplot again and plot my data. Here they are. I can skip this. I jitter them. So here's our function. And the function is in 2 colors, so it's not so obviously, but I can show it here. See, this is our logistic function. This is the estimated logistic function based on B1 and B0. And I color coded it here for you. And whenever the function here, just look at the function, not at the data at this point. Whenever the function has a value that is smaller than 0.5, it is red. And whenever the function has a value that is bigger than 0.5, it is blue. And that's important because if the probability for a white wine is bigger than 50%, we predict it as a white wine. So in the area here, everything right of the blue line is where the function is greater than 0.5. All these wines are predicted as white wines, and that's why they are made blue. And all the wines that are generate a function value like here less than 0.5, the probability for wine is less than 0.5 to be white, then it's obviously predicted as red. These are these wines here, and they are red. So what I can see here is what I could see in the confusion matrix. All the wines that have a value of 1 are white, and all the wines that have a value of 0 are red. That's how I coded them. So all the lower wines, the lower dots, are red wines. All the upper ones are white wines. Now let's see how they were predicted. These ones are all white wines. These ones here are predicted correct. And these ones are predicted false. Why is that? Well, because they are all white wines up there, but only the blue dots are predicted as white, while the red dots are falsely predicted as red, but they were white. These wines here are all red wines because they're down here. But only these ones here are predicted correctly because they were predicted as red, while these ones here are red, but they were predicted as white. And this is my arrow here. And you see, this is pretty much like my confusion matrix, except it's mirrored, but the logic is the same. And we can again see we did a pretty good job. Although these are the test data here. These are the training data, but most of the wines we got correct. We have to see how well we're doing on the test data because this is the only measure that really matters. What we see here could be a result of overlearning. So let's do that. But before I do that, I calculate the confusion matrix here for the training data. And you can see, yeah, it looks pretty good. These ones are predicted correctly from the training data. These were predicted falsely. So we did a pretty good job here. But again, this could be the result of overlearning. So let's look at the test data. What is the confusion matrix of the test data? Here it is. Wow. We only predicted this 23 and this 22, so about 45 records we predicted wrong. While more than 400 we predicted right. We used only one variable. We have no clue about wine. This is just machine learning. And if you look at the data, we can see we have an accuracy here of 90%. So 90% of all wines, of all 478 wines, were predicted correctly. From the white wines, which was our positive class, we predicted 90.8% correct. From the red wines, which was our negative class, the specificity, we predicted 90.4% correctly. So in this case, we did slightly better on the white wines than we did on the red wines, but pretty much the same. And we don't have the problem that we have predictions that are higher than 100% and predictions that are negative.